My name is Imaro Letugudo and I'm currently taking physics 2212 at Georgia Tech, and this is my lab report on the magnetic field of a bar magnet. Here are some key ideas that we need to know for this lab. The first being bar magnets, which will treat as magnetic dipoles, and as such we should be able to know the magnetic field of a magnetic dipole on its axis, as well as the fact that magnetic fields can be superposed, because this will be important as certain correct results will be obtained by removing the interference from the Earth's magnetic field. Another key idea in this lab is the purpose of computational modeling to visualize a magnetic field. And lastly, we'll need to know how to linearize data for this lab. The purpose of this lab is to determine the distance dependence of the magnetic field due to a small bar magnet. Here are some formulas relevant to this lab. The first two describe the magnitude of the magnetic field due to a magnetic dipole, something which will be important in calculating mu, the magnetic dipole moment of the bar magnet. The third equation has to do with the linearization of our data and will be applied in this lab. And the last equation defines approximately the magnetic field of a dipole at any location, something we'll use in the computational model. To the right, we have a look at our setup with lab. On the left, the first one, we essentially measured the distance for different px's and plotted this data as we'll see in just a moment. And on the right, we found the perpendicular distance needed for the magnitude of the magnetic field to be 100 microtesla, and then calculated the net magnetic field at the location shown in the diagram, which will later be compared to the results from the computational model. So here's a look at my experimental data where I have my raw data as well as my graph of lane Bx versus lane R. At the bottom, I have my net magnetic field as a location 45 degrees off axis from the dipole. Let's now use this data to perform some calculation. Here I've set the first two equations shown to the left equal to each other in order to find the symbolic solution for mu. I then pulled data from my graph as shown in this calculation, specifically n, which is the slope of the graph, and k is its y-intercept. I got negative 2.9476 for n, and k's value is shown on the left. Using these numbers, I solved for mu, and I got 3.205 newtons meters per Tesla. Only the first and fourth statements describe what I observed in my experiment. I noticed that when the magnetometer was far away from the magnet, Bx was close to zero, and that when it was brought closer, Bx increased as expected. Now for the computational model, the first thing I did was define a function for calculating the magnetic field due to a dipole with a given magnetic dipole moment and a specified observation location. I used the formula I mentioned earlier. I then set the locations for 6 of the 7 points where I'll be visualizing the magnetic field. 2 of these points are on the dipole axis, while the other 4 are perpendicular to the dipole axis. After that, I drew arrows for each of those 6 points as shown in the code here. And lastly, I did the same but for an observation location at a 45-degree angle off axis from the dipole axis. So here's the final result, which shows the 2 on-axis magnetic fields in orange, the 4 perpendicular magnetic fields in cyan, although only 3 show due to some discrepancies in the Etogodo theorem, and the 45-degree off-axis magnetic field in magenta. Note that the arrows are scaled proportionally to the magnitude of the magnetic field they represent, as would make the most sense. And also we also have the output, and the one we'll be most likely interested in is the one which shows the magnitude of the magnetic field at the 45-degree off-axis. Today we have two what if questions. For the first one, if we hadn't compensated for magnetic north and laid the meter stick at an intermediate angle, our results for Bx would have all been off by specific amounts due to interference by the Earth's magnetic field. Not only this, but since the magnetic field superposed, this would have adversely affected the magnitude of the magnetic field in the second part, leading to inaccurate results. For the second one, if we had stuck to magnets end to end, I'd expect the measurements to all be multiplied by some scalar constants, In other words, I'll expect more or less the same results but with different numbers, as everything, including the orientation of the magnet and the relative positions, will be the same, and the only real difference will be the magnetic dipole moment. This would just be like if we replaced our magnet with a stronger magnet and repeated the experiment. Thanks for watching.